I like to keep things real simple. And the basic premise, well, the target, I should say, the target of this procedure is to determine the molecular weight or the molar mass of an acid. What do you need to know to do the molecular weight? You need to know the mass and then how many moles that represents. That's the whole lab. Anytime we talk about we're doing molecular weight or molar mass, that's our target. So we need to find the mass and the moles of the acid. Okay, getting there is the fun part. So how are we going to do it using titration? Well, our acid is citric acid. Yeah, the sour in oranges. And it's got, let's see. Well, for our purposes, all we need to know is how many protons does it give up in a reaction? Like remember.
Citrus is called citruses because they have citric acid.
Yeah.
That's what I was saying.
Oh yeah. They also have other acids in, like ascorbic acid, which is vitamin C. It's a different structure than this. Citric acid actually plays a central role in the biochemistry of all cells, our types of cells, plant cells, whatever. You may hear it later. It's called the citric acid cycle, also called the Krebs cycle.
I've learned that about 2 or 3 times already now.
Yeah. Okay, so all we need to know is how many protons are in that acid. So I'll use Ca for abbreviation. That's the rest of the molecule. Right? And it's right here in the method. It's just easier for me to write it this way. So now that we know that's how many protons there are, when we titrate this acid against the base, then we can say something about the reaction. You have to know the stoichiometry before we can determine the number of moles. So the stoichiometry says that when we have this acid, and this is a water-soluble solid, so you can get the mass. You weigh a certain mass and you dissolve it in water. Then you do the reaction. So we're going to put this in an aqueous solution. And then we're going to titrate it with sodium hydroxide. So what happens? Well, these 3 protons attach to the hydroxyl. Right? But there are 3 of them. One of them is enough to make 1 water molecule. But if you got 3 of them, you're going to make 3 water molecules. So you need 3 of these to balance it. And then what do you have left? We have 3 sodiums plus the rest of the citric acid molecule. Okay. So that, in effect, is our titration equation. It's not a complete equation. It's right here at the bottom of the page. The importance of this reaction, it tells you that if you can find out how many moles of sodium hydroxide was required to neutralize that citric acid, then you can say something about how many moles that is. So we need a way to say how many moles, because when we start, we're going to use phenolphthalein as an indicator. Right? So under acid conditions, phenolphthalein is clear. Right? So it'd be clear for this acid. And when we titrate it, in other words, we're going to add enough solution to this solution to exactly balance to reach the stoichiometric point. When we do that, it's going to turn pink because it would be just over the equivalence point and give us a few of these. Not many, just enough to turn pink. It won't affect the calculations that much. Okay, once we know that, we know the volume here that was delivered. We know its concentration. So molarity times volume equals moles. We can say that's how many moles of base. Okay? So if we know the number of moles of base, how do we find the number of moles of acid? Well, if we know the moles of that. moles of base, moles of acid. What's the ratio? 3 of these to 1 of those. So if we find the moles of base, we take 1/3 of that, gives us the number of moles of acid. And it goes in here along with mass that we weigh before we put it in solution. We got our answer. Okay. The trick is we need to know the concentration of this sodium hydroxide to 3 digits, at least 3 decimal points. It needs to be accurate. The problem with sodium hydroxide is it's not stable. The solution is not stable over time. What tends to happen is sodium hydroxide reacts with carbon dioxide in the air and makes sodium carbonate. And it just precipitates. So we need to standardize our sodium hydroxide. We need to know its concentration. And we're going to do that by titrating sodium hydroxide with acetic acid. Okay. Acid-base reactions always produce water and the salt. This is in solution. This is liquid. Okay, so that's our standardization equation. So since this one has 1 proton and this one has 1 hydroxyl, the number of moles are equal. If we find the number of moles, if we know the number of moles of this one and add enough solution of this one to equal them out using our indicator, then we know that the number of moles here is equal to the number of moles there. And we know the volume that was dispensed. So moles per liter is molarity. Then we know our concentration for sodium hydroxide. So we have to do that one first. Then we take this standardized sodium hydroxide and use it in that titration. So we're doing 2 titrations. Okay. Now the skill is in doing the titration, because in either one of these, when you have that phenolphthalein, if you're not careful, when you get close to the end point, you can overshoot it. You can put too much sodium hydroxide in there and go way past. If you do that, then your calculations are off. So you can do it really fast in the beginning, but when you get down close to the equivalence point, you got to slow down and do it dropwise. And that's the tedious part. Okay, so let's see. Are there any pre-lab questions in here we need to deal with?
There's discussion questions, there's pre-lab questions, there's 4.
Discussion pre-labs. Okay. Yeah, we might as well do those. Rag. Oh, you still copying? Yeah, okay. Okay. So that was all theory. I think these discussion and pre-labs are going to be more practically oriented. Discussion 1. Calculate the volume of 0.750 molar sodium hydroxide solution required to titrate 25 milliliters of 0.873 molar acetic acid solution. Okay, we're using that sodium hydroxide acetic acid equation. We know that the number of moles of acid equals the number of moles of base because the acid produces 1 proton, the base produces 1 hydroxyl. So they're equivalent stoichiometrically. So what we can do is say that the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. because they're equal. Moles equals moles. So this one is really simple. The base is 0.750 molar. And it's saying calculate the volume of the base. So that one is unknown. And we're supposed to titrate against 0.873 molar acetic acid times its volume of 25 milliliters. We can use milliliters in here because this is a ratio. Volume on both sides will cancel. So our answer will come out in milliliters if we use it this way. We don't have to convert it to liters. And by the way, this is the standardized concentration for the acetic acid. That comes from the supplier. It's very stable over years. Okay, so if we do that calculation, let's see, where's my number cruncher? We just say this one times that one divided by this one. And I get 29.1 milliliters equals the volume of the base. And that should be, that is our equivalence point, the stoichiometric equivalence point. Okay, oh, this is a good one. Got it? Okay. Number 2. Now we want to know, calculate the volume of 0.75 molar sodium hydroxide solution required to titrate 1.20 grams of citric acid. Okay. We need to know how many moles that represents. Otherwise, apples and oranges. Right? This is mass. We need moles. So we need an accepted value for citric acid. And let's see, is it in the method? Should be in the method. Either that or we have to calculate it. I don't see it. I don't see it in your method. Let me see if I've got it already figured out. We're going to need a value to compare our data to. All right. That's okay. I think it's right. Here it is. Accepted value, 192.13. 192.13 grams per mole. That's the accepted value. So if we divide that into 1.20, 192.13, we get 6.25 times 10 to the minus 3 moles of citric acid. Okay. How many moles of sodium hydroxide are required to react with that many moles of citric acid? This one has 3 protons in it. Sodium hydroxide only has 1 hydroxyl, so it takes 3 times as much sodium hydroxide as it does citric acid. The ratio is it takes 3 of these for every 1 of those. So 3 times that value will give us the moles of sodium hydroxide required. which is 1.87 times 10 to the minus 2. Moles of sodium hydroxide. Okay, now let's go back to the question. What's the volume of 0.750 molar sodium hydroxide? So if this is moles, and moles per volume equals molarity, and molarity is given as 7.50 or 0.750 molar. Then to solve for this one, we need to put it over here and put this one over here. Right? Divide that value by 0.75. So that's 250. 250 2.50 times 10 to the minus 2 liters. So what would that be in milliliters? Well, milli, we need 10 to the minus 3 here to make our milli, right? So what if we make this 10 to the minus 3? What does that make this one? It means 25. So milliliters would be 25 milliliters. Okay, 25 milliliters of this sodium hydroxide solution should titrate to neutrality that many grams of citric acid. Okay, that was discussion number 2. Okay, we're going to do pre-labs maybe. See what they have to say. Pre-labs are probably pretty simple, as I recall. Calculate the molarity of a sodium hydroxide solution. If 24.3 milliliters were required to titrate 25 milliliters of 0.7873 molar acetic acid solution. This goes back to the same relationship between sodium hydroxide and acetic acid. One proton from the acid, one hydroxyl from the base. So the number of moles are 1 to 1. That being said, we can say this. Right. Number of moles of acid equals the number of moles of base, which is this calculation. So in that case, we can say 24.3 milliliters of sodium hydroxide. Okay. And this is our unknown, right? Base. The volume of acetic acid is 25 milliliters. And 0.873 molar. So we just solve for the molarity of the base.
0.898. 0.9 if you want around there.
Do what?
I did it.
Oh, okay. Saving me the trouble. Thank you. What was it?
It was 0.90 if you want to round up.
Give me 3 significant figures.
0.898. That goes for 1, so I just round it.
Yeah, 0.898 molar solution. Yep. Okay. Does that really make sense? If it takes less volume to match the moles, then the molarity should be greater. Yeah, that makes sense. Okay, that was number 1. Let's look at number 2. Let's see. Calculate the molecular weight of citric acid. Oh, okay. So this is what we're going to be doing. Oh, wait a minute. We just did this one in reverse right before that. 25 milliliters of 0.75 molar sodium hydroxide are required to titrate 1.20 grams of citric acid. We just worked that discussion number 2 in reverse. Now we'll do it. So, citric acid, let's see, 25 milliliters of, let's see, we're going to have to end up with moles, so we've got to change it to liters. 25 milliliters of base equals 0.0250 liters of base times the molarity of the base, which is 0.750 molar. So that'll give us the number of moles of base. (1.875 times 10 to the minus 2). 1.875 times 10 to the minus 2 moles of sodium hydroxide. So how many moles of citric acid does that represent? Right, the ratio is 3 to 1, right? So if we've got this many moles of sodium hydroxide, this actually is 3 times the moles of citric acid, because 1 mole of citric acid requires 3 of those.
So it was the 6.25 times 10 to the negative 3.
Yeah, this should divide this by 3. 6.25, 10 to the minus 3. Divided by 3, 6.25 times 10 to the minus 3. And that's the moles of citric acid. So grams per mole, we just have 1.20 grams. Divide that into 1.20. 192. 192 grams per mole. Okay, so we just work that same problem backwards. Okay, so let's see. Well, you got your lab notebooks with you? Okay. Mark off a place to put the data in. Right, leave space for the rest of it. I'm not going to check it because I forgot to give this one to you. So part 1 is standardize the sodium hydroxide solution. Part 2 is titrate citric acid. And then we have post-lab questions. I'll read those to you guys.
What should I do with this again?
Oh, just put your title in there where it's supposed to be and put it in your table of contents. And then skip enough space so that you can fill in the other information. Then just make a data table for the information you're going to need.